This Year 12 maths lesson is to do with using natural logarithms. So it will become clear in a bit what I mean by natural logarithms, and it ties in with chapter 14.7 in your Pure textbook. Now we've done quite a few lessons on exponentials and logs, so we're getting towards the end of it now. So we've done a variety of sketching the graphs, differentiating e to the x, modelling using exponential functions, then the important bit to do with what was the relationship between exponentials and logs. Then you went on to the log laws, and the importance of those was to do with solving some equations where you have the unknown in the power. And now what we're going to do is we're going to have a look specifically at natural logarithms, before we then go on and look at how natural logs tie in, or logs in general tie in with some graphs, which will be our last lesson next time. Okay, so first of all, let's have a little quick recap about what was special about e to the x. Now e, remember, this is an exponential function, but e is the base number. Now if you remember what e was all about, okay, so e was a value around 2.718, okay, and what was special about e, we'll talk about that in a minute, but the base number e is called Euler's number. So the mathematician Leonhard Euler came up with this as a number, and found that when he was investigating and looking at things within nature, things to do with exponential growth and decay, he found that things tended to grow and decay at this rate. So at the rate with this being the base number for the exponential function. So it is a very, very important number. Let's talk about why it's important sort of from a mathematical point of view. If you remember when we did differentiation of e to the x, okay, I told you that if you differentiate e to the x, then you get e to the x, so it stays the same. We did also talk about differentiating something like e to the 3x, and you remember what we had for that. We had, you still get the e to the 3x, but then you also get a number 3 at the front because you differentiate the power at the front there. But if you think about differentiation, now differentiation, what that's all about is that's the gradient function for the original function that I started with. So what is special about the value of e is that when you draw the graph, okay, the gradient of the graph at any point has the same value as the original function. Okay, so basically its rate of change, okay, is proportional to the original value of the function. Okay, and we can have a think about, more of this will come out next lesson, but we can have a think about why that might occur in nature if you think about something like population growth. Now, population is going to grow according to how many people there are in that population. So the rate of growth is going to be proportional to how many people there are. So hence you're going to get its growth is a function of e to the x. So that kind of thing is quite important for you to understand. Okay. Now, the reason I'm talking about e to the x, okay, is we're going to be going on and talking about natural logarithms. Now, do you remember when we talked about our original logs? If I had 2 to the power x equals, say, 8, then when we wrote that in log form, we said log to the base 2 of 8 would equal x. So what it says is, what power do I raise the base to get 8? So the answer would be x equals 3 for that. So you remember that ties in with our logs. Now we're going to have a look at similar logs, because at the end of the day this is an exponential function in the same way that this is an exponential function, but its base number is e, 2.718, etc., rather than 2. So because it is a very, very special number, rather than writing log to the base e, we write that in a different form called the natural log. Okay, and the reason it's called the natural log is because it occurs in nature. So let's have a look at that then. Right, so let's just recap then. If we have y equals e to the x, or I can write it round that way, e to the x equals y, we're very good at then writing the equivalent log form. Okay, so you need to be writing this down, I would say. So if e to the x equals y, then what that says is log to the base e of y equals x. So remember, it's what power do I raise the base to get y. Okay, so when I have a look at that, so you look, we've gone from y equals e to the x to x equals log to the base e of y. Okay, so what that tells you is that this and this are inverse functions of each other. Okay, that's just a little recap about how log works. So the inverse function of e to the x is basically log to the base e of x. But because this occurs in nature so much, this log to the base e, we give it its own special notation, okay, ln x, all right, and how you say that, make sure you say it properly, it's ln, so it's ln of x. So ln of x is known as the natural logarithm, and it's the inverse of e to the x. So if we have something involving e to the x, and I want to get back to what the original value is, then we use ln. Okay, now let's have a look then. So here you go, e to the power ln x is ln of e to the x, and that's equal to x. Reason being, if you think about that, do you remember our log laws? With this one, we could bring down the power and write x ln e. Now do remember, ln is the same as log to the base e. So this part here is saying, what power do I raise e to get e? And the answer is 1, so you can see how that is equal to x. Okay, now let's have a look at the graph. We do sometimes get asked to draw graphs of log functions. We've not really drawn many of them before, but we know that exponentials and logs are inverses of each other. If you remember back to when you were looking at inverse functions within GCSE, how we get the graph, okay, is we take our original graph, e to the x, and we reflect it in the line y equals x, okay? So if you're asked to draw your log graph, so here's my exponential graph, here we go, so I would make a sketch of this. This is what my exponential graph looks like, y equals e to the x. It looks like any other exponential graph. It goes through the y-axis at 1, it's never below the x-axis, okay, and it goes, it's very, very small for negative values of x, and then gets very, very big quickly. If I dash in the line y equals x and I draw my ln graph, okay, my ln graph is going to look like this. Now, a few important things to notice. It goes through the x-axis here at 1. And the other thing to notice is that there's no values for your ln graph, okay, within the negative part of the x-axis. So basically, and we've talked about this before, logs do not like negative numbers, so you cannot do log of a negative number. If you try and put it in your calculator, it will say maths error. Now, you know on your calculator, we've got the log function. If you have a quick look at it now, if you go 2 buttons below the on button, you will see the ln button. It's just next to the log button. So if you're doing natural logs, you make use of that ln function there. Okay, so what we can do, and this is what we're going to be doing a bit of today, a bit like you were solving equations last lesson to do with exponentials with different bases, we're going to do exactly the same thing, but here our exponentials are going to have base e, and so the logs we're going to use are going to be natural logs or ln. So let's crack on with a few examples then. If you need to pause to write that down, then please do. Again, we've not really drawn log graphs before, so do make sure you understand what log graphs look like. This would be exactly the same, you know, if I drew the graph y equals, say, 2 to the x. If I was asked to draw the graph log to the base 2 of x, it would look very similar to that. Okay, so remember the shape, remember where it goes through on the axis. Okay, right, first examples to have a look at them. So solve these equations giving your answers in exact form. So let's write down the first one. So if we know that e to the x equals 5, okay, then what we're going to do, in the same way as we did when we had things like 2 to the power x equals 5, we're going to do exactly the same thing and write that in equivalent log form. Okay, so remember what logs are. What power do I raise the base to get 5? Okay, or what power do I raise the base to get 5? So in this particular one, we would normally write log to the base e, but remember we don't write log to the base e, we write ln, and we write ln of 5. Okay, remember that's exactly the same as x equals log to the base e of 5, but because exponential growth and decay with e as its base happens so much, it has its own special notation, ln 5, and you can put that in your calculator. Let me quickly put that in my calculator now, and it comes out as 1.609, blah blah blah. But when we want to leave things in exact form, we will leave our answers as ln of something. Okay, let's have a look at this one then. We're going to write this in our equivalent exponential form. Okay, so what this says, remember what your log is, it's what power do I raise the base, well, this is, I raise the base to this power, and that gives me x. So x is going to equal, remember with ln, my base is e, so x is going to equal e cubed. And again, that is in exact form. Okay, you can put it in your calculator. Remember where your e button is, alpha, and then the times 10 to the x. And if I do that to the power 3, I get 20.0855. Make sure you know where that is on your calculator, but we would leave it in exact form like that. Okay, so just make sure you understand it's exactly the same as we did with logs to different bases, but here we're using base e and we're using ln rather than log to the base e. So do make sure you're happy with those. Okay, let's look at some more complicated ones then. Right, so for part A here. Now this is very similar to the one we did on the previous slide that said e to the x equals 5. We wrote x equals ln 5. So exactly the same as that. Okay, so but in this situation, the power is going to equal ln 7. Okay. Now, if you're happy to go straight to that, then that's fine. If you're happier, so I'll just put a little all there. If you're happier always thinking, well, if I want to solve that because the power has x in, I take logs of both sides. This is the other first step you can write if it makes it a little bit clearer for you. Take logs of both sides. Using our log laws, we can bring down the power. Okay, and then remember, because ln is log to the base e, this part here is equal to 1, so we get 2x equals 3, 2x plus 3 equals ln 7. So if you want to write those steps out, if that makes it a little bit clearer for you, then I'm happy for you to do that. If you can go straight from A to that, again, I'm happy for you to do that. Okay, right, so here's where we've got to. I now need to rearrange that to be x equals, okay, so take the 3 over, ln 7 minus 3, so x is equal to a half ln 7 minus 3, and you leave that in exact form, okay, because that's what the question says, so in exact form. Okay, part B then. Now, we know from our previous questions that had ln x equals 3. So our previous one said ln x equals 3, and we knew that meant that x equals e to the 3. Now, before I can do this unlogging, I must make sure, first of all, okay, that I just have ln x equals something. So I mustn't have lots of other numbers here. I can't do e to the power this, e to the power that. Okay, I must rearrange it first. So I want to rearrange, remember, to just get ln x equals something. So if I do -1 to both sides, and then I divide by 2, I get ln x equals 2. So now it looks very similar to the one we did on the previous page. So x is equal to e to the 2. So that's my answer. So here's the really important bit for this. Before you do e to the power, you must make sure you just have ln of something with no numbers around it. And the same here, you must make sure that you just have ln of something, okay, before you go and do, oh, no, that's all right. So that's fine. That was just writing out the extra step. Sorry, I got a little bit lost there. Okay, so for part B, do make sure you just have a ln x equals there. Okay, right, let's look at this last one. Okay, now I'll just write it out so you can see it. E to the 2x plus 5e to the x equals 14. Now that looks rather complicated, but have a think back to what we were doing in solving equations in the last lesson. Okay, when we were solving equations in the last lesson, we had equations that looked like this, okay, but they looked like 2 to the 2x plus 3 times 2 to the x equals 14, something like that. And we had to recognise those. Do you remember? We had to recognise those as a quadratic equation or a hidden quadratic equation. So this is exactly the same form. If I bring that 14 over, then what I've got here is I've got a constant, I've got 5e to the x, and then I've got whatever is here, e to the x, I've got it squared because that's the same as e to the x all squared. So this here is a hidden quadratic. Now, if you remember when we were solving those last lesson, I said you could use a substitution if you wanted, or you could just straight away write it into brackets. Now, these will usually factorize. So if you want to use a substitution, fine. I think with ones like this, because you know that the thing that's equivalent to your x in a normal quadratic is e to the x, I reckon you're all good enough to just be able to factorize it like that. If you do want us to do a substitution, then let y equal e to the x, and then you get y squared plus 5y minus 14 equals 0, etc., etc. But I do reckon that you can probably go straight from that to factorising. Multiply to give minus 14, add to give 5. So what's that going to be? A plus 7 and a minus 2. That works? Okay. So if we look at our brackets here, we've got e to the x equals minus 7, and we've got e to the x equals 2. If you've done your substitution, you have got y equals minus 7, y equals 2, and then you would have put your y back in for e to the x. Okay, now think about your e to the x graph. Do you remember what it looked like? It went like that. So it is never negative. Okay, so that is basically impossible. Remember, we had some of these before. So I just ignore that one. It's impossible because e to the x is always positive. So the only one I've got to solve is this. E to the x equals 2. So take logs of both sides, x equals log 2, and you leave your answer in exact form like that. So there's just one answer for that one. Okay, right, on to some slightly more complicated ones. So let's have a look at these two here. Right, let's have a look at this first one here. Okay, so part A. 3e to the 2x equals 2. Okay, now you know that if I've got the x in the power, then I'm going to want to take logs of both sides. Now, just be careful, okay? Before you take logs of both sides, I would recommend just having your e to the 2x on its own here. So the first step, okay, is to divide by 3. Now I can take logs of both sides, natural logs, because the base is e. So if I natural log that side, I get ln e 2x, ln e to the 2x, so that gives me 2x. And if I ln that side, I get ln of 2/3, and I just write it like that. Best as a fraction, okay, because it's not a very nice decimal. And so then my final thing to get my final answer is I write half ln 2/3. Okay. Now you can, if you want to, okay, do basically take logs of both sides before you do that rearranging. So I will just show you that just in case that is something. Let's just pop it as an or at the bottom. If I do take logs of both sides, I get ln of 3 e to the 2x equals ln 2. Now using your log laws, this is a product. So I get ln 3 plus ln e 2x equals ln 2. So then if I take the ln 3 over, I get ln e 2x equals ln 2 minus ln 3. And then remember again with your log laws, I am at an angle here, aren't I? But never mind, you get those, that minus that gives you ln 2/3. Ln of e to the 2x is just 2x. So can you see I've actually got the same thing here as I've got here. But I reckon it's probably easier to do your rearranging before you take logs, okay, but matter of preference. Now, this next one's an interesting one. Examiners seem to really like these, because it just looks a little bit different. Okay. Now, if you're looking at that, you might think, don't quite know what to do with that. So, if I was there in the classroom and nobody knew what to do, what I would do is I would write it like that. E to the minus x, 1 over e to the x. And then I would say to you, what do you think you would do now? Hopefully, somebody, a bright spark in the class, would say, well, I know when I've got anything as a fraction there, I quite often want to get rid of fractions by multiplying through by it. Multiplying through by it, let's see what happens then. E to the x times e to the x gives you e to the 2x. 3e to the x. And when I times that by that, I get plus 2. Look at what we've got there. That now is a hidden quadratic, and a quadratic equation in e to the x. So similar to the one we did on the last page. So I'm going to factorize. Do your substitution. Let y equal e to x if that's easier for you. Multiply to give plus 2, add to give minus 3, minus 2 and minus 1. Hopefully you'll agree with that. So two answers, e to the x equals 2, e to the x equals 1. Okay, both valid answers because they're both positive. This one gives me x equals ln 2, leave it in exact form. This one here, x equals ln 1, you can put it in your calculator if you want. Ln of 1 is 0, that's where it goes through the axis. Think about why that makes sense. E to the power 0 equals 1. So we get two answers for that one. Do remember this one. Okay, it's one of those ones, a bit like in GCSE, where examiners always loved to ask you to factorise the difference of two squares because it's just a little bit different. They love this one. So do remember, because it is a little bit different, what you need to do. First step, multiply by e to the x, then it becomes one of these hidden quadratics. Okay, we've got one more to do. Wow, how nice is that? The only reason I've done one like this is there is one like this in the questions that you're doing, okay, and just want to make sure that you sort of know how to attempt that one. Now, in the question that's in the exercise, it does say give your answer in this particular form that involves luns. You know that when you've got powers that have x or the unknown in the power, you're going to take logs of both sides. You might question here, okay, which base am I going to take logs of? The question in the textbook sort of says give your answer in the form, and it's got luns in it, so that should prompt you that you're going to do lun of both sides. Now remember, when you do lun, it's lun of all of that side equals lun of all of that side. You never do separate lun, lun, lun. It has to be lun of all of the left hand side equals lun of all the right hand side. Okay, let's have a look at what we can do now. Log laws. This is a product. Remember, with your log laws, you can split it as ln 4 to the 2x plus ln e to the 3x plus 1. And I'll just leave that as ln 6. Let's have a look at this bit here. Now, this is the benefit of taking logs. Remember your log law, you can bring the power down. So that's the same as 2x ln 4. Now, what's good about this? I can bring the power down, so I can get 3x plus 1. But I get 3x plus 1, let me write it for a minute, ln e. Now, ln, remember, base e, so ln e, that is equal to 1, and that equals ln 6. So now, I'm solving the equation. So what I want to do is I want to gather all of the x's together on one side and all of the non-x's on the other. Okay, so this has got an x in it, so I'm going to leave it there. This has got an x in it, so I'm going to leave it there. And what I'm going to do is I'm going to take this plus 1 over the other side and make it a minus 1. Now, algebra skills, take out x as a factor. X times 2 ln 4 plus 3. These are like the GCSE most complicated change in the subject questions that you used to do. Final step. This is something in a bracket all times x, so I just divide by it. Okay, now depending if it asked for it in a particular form, it might have asked it in the form, say, ln a plus b over ln c plus d. If it did, I would then need to just make sure that the bottom has just a ln. Okay, 2 at the front comes up as a power, so that's going to be ln 16 plus 3. You'd only bother doing that if the question had asked it in that particular form. Okay, right, so that's the most complicated one, so make sure you're happy with that, make sure you've got those written down. Do rewind, rewatch through the video if you're not sure. Okay, over to you then. Exercise 14G, page 327, questions 1 to 8, quite a few questions. It's important you do all of them though. Okay, I've not asked for any of those to be submitted. Now, tomorrow's lesson is going to be our final lesson on exponentials and logs. It's to do with some graphs of nonlinear functions. Okay, so today I'm going to give you homework assignment 18 as well. Okay, I think what I'll probably do is I will attach it to Insight, but I will also load it up in Teams as well as a file. So up to you which place you want to get it from. Okay, and this is going to be, this homework assignment 18 is going to be what I'm going to be asking for you to submit. It's likely to be over more than one page. The actual assignment itself is a couple of pages. Okay, don't write your answers on the question paper unless you feel you do have enough room to show clear working. Okay, I'd probably recommend to do them on a piece of paper and just try and fit it perhaps on a couple of sides, but write out the question first. And then those I would like to be submitted, okay, on Teams. So load them up onto Teams. I'll be setting it as an assignment, and then I'll have one of those Word documents that you can cut and paste your images into. Okay, that then will be the end of your Year 12 work. So we will have a talk about that homework assignment 17, homework assignment 18. And then what we will do is we will kick off your Year 13 work. I will also be uploading the the schedule for the Year 13 work, so it tells you what topics you're doing and in what order you're doing them. I'll put that on Teams as well. You probably want to try and print that out if you can and have it at the front of your folder, just to show the things you're doing and the order in which you're doing them. Okay, so any problems or issues, please do get back in touch with me. If you need any clarification, I would say watch the video again. Okay. Thank you.